Now I'm going to show you how to make your own stem and leaf plot. And this example says the following data represent the number of grams of fat in breakfast meals offered at McDonald's. Construct a stem and leaf plot of this data. So let's just look at this first. We have 24 data values here. They all are 1 or 2 digit numbers. And remember that we said the leaf in each value would be the rightmost digit and the stems would be any digits that came before that. So in this case, for this 12, the leaf is going to be 2 and the stem is going to be 1. In this case, for the 27, the leaf is going to be 7 and the stem is going to be 2. Here is a 1-digit number. So in this case, we do the same thing. The leaf is the ones place and the stem is anything that came before. Only you can see here nothing actually came before, but we have to use something. So in this case, the stem would be 0. So for each of these numbers, the stem is what's in the tens place. It's a really common misconception for people to think that the stem here ought to be 3, but the leaf has to be the rightmost digit. So the stem here actually does need to be 0. So now let's see which stems we need. We know we need a stem of 0, and we can see that our largest value is 59. So we need a stem of 5 as well. So you can't leave any stems out, so we need all the stems between 0 and 5. So what I'm going to do is I'm going to draw a vertical line. I'll put the stems to the left of that vertical line and the leaves to the right. And the stems are going to be 0, 1, 2, 3, 4, 5. So this line will hold our single-digit numbers. This line will hold our teens. This one our 20s, 30s, 40s, and 50s. Okay, now remember that also they said for a stem and leaf plot, the leaves must be in order from smallest to largest. That's a little too much to worry about when you're first just trying to get the data sorted. So what I usually do is I just get the data sorted onto the right lines, and then I make a new plot where I put all the leaves in order. So let's go ahead and do that. We'll start here. It's a lot like making a frequency table in a way, only instead of putting tally marks, we actually put the leaf digit. So for the 12, I'm going to go to the ones line and put my leaf down, which is 2. For the 27, I'm going to go to the 2 line and put my leaf down, which is 7. For the 51, I'm going to go to the 5 line and put my leaf down, which is 1. And then we'll go back up to the top and do the next column, and we'll continue till we have them all finished. So the next one is 22, so I go to the 20s line and put down a 2. Then 31, so I put down a 1. Then 55, so I go back to the 5s line and put down a 5. Now notice that I'm not putting a comma or a space of any kind in between the leaves. Since leaves always have to be a single digit, there's no need to put a comma between them. So we usually just list the leaves number after number like you see them here. Okay, now the third column, 27, 11, 59. So we'll have a 7 and a 1 and a 9. And now the next column, we have a 3, so we'll have on this line a 3 and a 16, so we'll have a 6 here, and another 16, so we'll have another 6 here. And so now you can see the answer to a question you may have had, which is, if we have a leaf repeat, do we need to write it down again? And the answer is yes, because you can see here that somebody who knows how to read the table will look at this and say, oh, the original data set contained 2 16s. Where if we only put the 6 down one time, nobody will know that there were originally 2 16s in the data. So do put the leaf down for each individual number in your data set. And then 25, so we'll have a 5 here. 21, so we'll have a 1 here. And 36, so we'll have a 6 here. Then 30, 32, 30 again. 32, 22, 9, so on the 0 line we'll have a 9, and 37, and 46, and 24. And this is not quite our stem and leaf plot yet. The only thing that's missing is we need to put the leaves in order. So what I'm going to do is make myself a new vertical line and recopy the stems and go back and put each line of leaves in order. So this line would be 3, 9. This line would be 1266. This line would be 1224577. This line would be 0012267. This line, of course, is just 6, and this line is 159. And then we need to put a legend that tells the reader how to read this stem and leaf plot. So we'll just say a stem of 1 and a leaf of 2 means a value of 12. And that's how you make a stem and leaf plot. So what does a stem and leaf plot do for us besides helping us get the data in order? Well, a stem and leaf plot is a sort of a quick and dirty histogram, and it allows us to see the shape of the distribution. In other words, it allows us to see whether most of the values are concentrated in the middle of the histogram or toward the left end or toward the right end of the histogram. The way this works is that each stem acts like a class of a histogram. So here is the stem and leaf plot that we made just a few minutes ago. And now what I'm going to do is turn it on its side. And you can see that the shape sort of goes up in the middle and then it comes back down. So we'll have a name for that in just a few minutes. But you can see that most of the values are concentrated in the 20s and 30s. And the more extreme values like the single digits and the 50s, there aren't as many of those as there are 20s and 30s. And one nice advantage of a stem and leaf plot over a histogram is that the stem and leaf plot retains the original data. See, somebody could still look at this stem and leaf plot and see that the original data contained a 21, a 22, another 22, and so on, and you just can't do that with a histogram. Now remember that when you make a stem and leaf plot, all of the leaves must be listed in order. If there are a lot of leaves, this can become tedious because it just takes so long to put them in order. So to save time, remember that you can use the sort A function on your calculator to speed things up. Now, another thing to remember is that if all of the data are not rounded to the same place value, you must round the values first before you start making the stem and leaf plot, because we need for all the leaves to be in the same place value. Now, speaking of place value, consider this data set. Here we have a set of 40 numbers that represents the 5-year rate of return of mutual funds, and all of these numbers have 2 decimal places. So some of these are 3-digit numbers and some of them are 4-digit, but they all have 2 decimal places. And I believe our smallest number is the 3.27 here, and our largest number looks like this 12.03. Now remember that if we were going to make a stem and leaf plot with this data, the leaves would only be the numbers in the hundredths place, and so the stems would all be either 2 or 3 digits. The number of stems required to make a stem and leaf plot of this data would make the plot useless for summarizing the data, because we would have to start with a stem of 32, and we would have to include every stem from there up to 120. Remember, the leaf can only be the rightmost digit. So that would mean our stems would go 32, 33, 34, etc. I didn't even have room to write all of the stems because we would have had to go all the way up to 120. And then you can imagine each line would only have had 1 or 2 leaves on it, and most of the lines wouldn't have had any leaves on them. So the stem and leaf plot in this case would actually do more harm than good. However, think about the fact that we could round this data off to where it all only has 1 decimal value. So 3.27 could become 3.3, and 5.38 could become 5.4. Let's look at that data. Here is the same data rounded now to 1 decimal place only. And now not only will it be easier for us to make the stem and leaf plot, it will be a lot more useful than it was. I've already got the stems laid out here. The stems will now go from 3 to 12, and I won't drag you through the process again of putting each leaf down individually, but I'm going to take you straight to the finished stem and leaf plot. And let's remember that we also need a legend so that somebody reading this table knows what the original numbers were. So we would need to say something like a stem of 3 and a leaf of 2 is equal to a value of 3.2. Okay, here's what the finished stem and leaf plot would look like. So you can see that if we turned this stem and leaf plot on its side so that the classes run along the bottom, the two leftmost bars would be by far the tallest, and then after that, as we go to the right, the height of the bars drops off quite a bit. Now, it's not very common, but we can split stems. Here is a data set where the stem and leaf plot is not very useful because we have so many leaves on each line. So when this happens, if we want to spread the data out a little more, what we can do is have two lines for each stem. The first line would contain the 0 through 4 stems, and the second line would contain the 5 through 9s. So that's what I've done here. I've got two lines for each stem, and I'm just going to copy all of the 0 through 4 leaves onto the first line and all of the 5 through 9 leaves onto the second line. And that way each line only has 5 possible values on it. Okay, this line would contain all of the 0 through 4s, and the next line would contain all of the 5 through 9s. And here again, all of the 0 through 4s, and then all of the 5 through 9s. And then you can see there aren't any 40s that are 0 through 4, so that line stays blank, and then we have 46 and 48. And then we would need to include something that tells the reader how to read the stem and leaf plot. So I've got here a stem of 2 and a leaf of 4 equals a value of 24. And there's no particular number that you have to choose here. I just happen to pick 24. And the last type of graph that we're going to look at in this section is called the dot plot. Now, a dot plot is another histogram substitute that is most appropriate for discrete data with a small range. Any data that can be grouped using single value grouping is easy to put in a dot plot. To draw a dot plot, all you do is make a horizontal number line, including every digit from the smallest observation to the largest, and then place a dot over the observation each time it occurs. And this is just another way to get a quick look at the shape of the data. So we'll draw a dot plot for this data that you may remember from the beginning of the section. First, I need to find the smallest and largest values, and it looks like the smallest value is a 1 and the largest is 11. So I need my number line to go from 1 to 11. Okay, now I'm going to put a dot over the appropriate number for each value in the data. So here is a 7, so I'll put a dot over the 7. And here is a 5, so I'll put a dot over the 5. And a 2, then a 6, then a 2. Then my next column is 66752. Then the next column is 66159. Then 611237, 44475, 65859, 27248, and 66665. So you can see how this mimics a histogram where each class is just a single value, and clearly our tallest bar would be the 6. Now, it's very important that you include every value between the smallest and largest observations, even if that value does not appear in the number set. We just cannot leave numbers off of the number line. If that number is there and it has no dots, that means that class is empty. That information is just as important as knowing that there are lots of dots in a particular class. So never leave a number out just because it's blank. Now let's talk about how to identify the shape of a distribution. And in some ways, this is the most important concept in this whole section, because we're going to be talking about the shape of a distribution all throughout the rest of the class. So it's very important for you to latch on to this idea. The reason the bars of a histogram are connected is so that we can get a feel for the shape of the distribution. Understanding the shape has important implications for the inferential methods that we'll be learning later. Identifying the shape of a distribution is subjective, and that means that in some cases people might disagree about the shape. Now, I don't want you to worry, because the distributions that we would ask you about on quizzes or tests will be pretty cut and dried. but not all of them are, and it's possible in some cases for people to disagree about the shape. Classifying shape makes sense only for quantitative data, because with qualitative data, they can be put in any order and that would change the shape. So remember that these shapes are generalities. Not every histogram we have will look exactly like one of the diagrams you're about to see. Okay, first we have what's called a uniform distribution. Uniform because all of the bars of the histogram are about the same height. Now they won't be perfectly the same like you see in this diagram, but they would be generally the same. And usually that just means there's no drop off as we go toward one edge or the other. This is an example of a bell-shaped distribution. You can see that if we were to draw over the tops of the bars, you would get a shape that looks somewhat like a bell. The tallest bar would be approximately in the center, and there would be shorter bars on each end. Now this histogram represents a data set that is skewed right. You can see when we draw the little general curve over it, it has a tail that trails off to the right side. And what's happening is these large extreme values are pulling the mean of this data set up. So we say that it is skewed to the right. And this data set is skewed to the left. And you can see that it has a tail that trails off to the left. Okay, so let's practice identifying the shape of each of these distributions. And remember, these are generalities. So it often helps to draw the little general curve over the top and see if there's a tail, and if so, which way is the tail going. For this first data set, I would say that the tail is trailing off to the right, so that's skewed right. The second data set, you could almost argue that it's bell-shaped, but notice that from the tallest bar, there are only 1, 2, 3, 4 bars that are bigger than that, but there are 1, 2, 3, 4, 5, 6 bars that are less. So I'm going to say this data is slightly skewed left. And then this data is approximately bell-shaped. It's not perfect. From the tallest bar, we have 1, 2, 3, 4, 5 bars to the right, but only 4 bars to the left. Somebody might argue that it's very, very, very slightly skewed right, but I would say that this data is bell-shaped. Don't get into a forced habit of counting the bars. I just use that to give you a feel for what's going on. But because this 5th bar is so short, I'm going to say that this data is bell-shaped.